Welcome back, everybody. Learning is a hobby here. I wanted to record my video on my solutions for Terence Tao's Analysis 1 book. We're going to finish up Chapter 3 here. So this is my solutions for Section 3.6, which is the last section in Chapter 3 for Tao. And let me just say that I've recorded this video already, the entire thing. This is the second time I'm recording it because the first video, for some reason, didn't record any of the audio. So if you saw the first version of this that I recorded without audio, I apologize. I'm redoing it now. So while it's annoying, the audio wasn't recoverable. So I guess I'm just gonna redo it. So here we go. All right, let me bring up the solutions. Okay, starting with problem 3.6.1, he asks us to prove proposition 3.6.4. Just to remind you what that proposition says, it says that the cardinality of two sets being equals an equivalence relation. So that's what we want to show here. So we need to show that it's reflexive, symmetric, and transitive. All right, so here's my proof. Let x, y, and z be sets. All right, one will show that it's that equivalence of cardinalities is a reflexive, has the reflexive property. So let I sub x be the identity function on x, then obviously x equals ix of x equals iy of y equals y. So that implies that x equals y. And for any x in x, the identity function on x of x is equal to x, therefore I sub x is a bijection, therefore x has equal cardinality with itself, so it's a reflexive operation. Right, then we want to show that it's symmetric. Let x have cardinality with y, then there's a bijection f from x to y. Since f is a bijection, f inverse from y to x is also a bijection, therefore y has equal cardinality with x. Right, so that shows symmetry. Then finally, transitivity we have to show. Let x have equal cardinality with y and y have equal cardinality with z. Then there exist bijections f from x to y, g from y to z, such that then if we make the function g composed with f from x to z, it's a bijection by exercise 332. Therefore, x has equal cardinality with z. Right, so that shows that it's an equivalence relation. Okay, next problem, 362. Show that a set X has cardinality 0 if and only if X is the empty set. And here, it follows from the fact that the only function f from the empty set to x that's a bijection is the function where the codomain is the empty set. So you can see my solution to exercise 333. All right, next one, 3.6.3, let n be a natural number, and let f from the set of natural numbers between 1 and n to the natural numbers be a function. Show that there exists a natural number m such that f of I is less than or equal to m for all I between 1 and n. He gives a hint here. He says induct on n. You may also want to peek at lemma 5.1.14, which I won't bring up here. We haven't gotten up to chapter 5 yet, but anyway, the proof follows the way that I did it. So thus, finite subsets of the natural numbers are bounded. Use this to give an alternate proof of theorem 3.6.12 that does not use lemma 3.6.9. Theorem 3.6.12 says that the natural numbers have infinite cardinality. All right. So let's start with the proof of the first part here. Show that finite subsets of the natural numbers are bounded. So we proceed by induction on n. So here's my base step. Let f from the singleton set containing 1 to the natural numbers be a function. Then there is a natural number n such that f of 1 is n. Then n is obviously less than its successor, so it works. Then we move on to the inductive step. Assume there's some natural number n such that for any f in the set going from the set of natural numbers from 1 to n to the natural numbers, there's a number f sub f, a natural number, such that f of I is less than or equal to mf for each I between 1 and n. Then consider a function g from the set of natural numbers between 1 and the successor of n to the natural numbers, and then define the function g hat to be the function that goes from the set of natural numbers from 1 to n to the natural numbers, such that g hat of k is equal to g of k for k between 1 and n. Then there is a number, and an upper bound for all the numbers there. So m sub g hat, I'm calling it, such that g hat of k is less than or equal to m sub g hat for all k between 1 and n by the inductive hypothesis. Then either g of the successor of n is less than or equal to m sub g hat, or g of the successor of n is equal to m sub g hat, or g of the successor of n is greater than m sub g hat by trichotomy. In the first two cases, m sub g hat works. In the last case, just take the successor of g of the successor of n, and if you take that as m sub g, that works. Okay, and then we can use that to provide an alternate proof of proposition 3.6.12. Remember, that proposition says the natural numbers is infinite. The set of natural numbers are infinite. Okay, and I did this with a proof by contradiction. So assume n has finite cardinality, then there's a bijection from the set of natural numbers between 1 to n to the natural numbers for some n and n. Since f is surjective, the forward image of the set of natural numbers from 1 to n the forward image of the set of natural numbers from 1 to n under f is equal to the set of natural numbers. However, by the above proposition, f of I is less than or equal to m for some m and n for all I from 1 to n, then the successor of m is not in the forward image of the set under f, which contradicts that f is surjective. Therefore, n cannot have finite cardinality, which means that n has to have infinite cardinality, and that's the proof. Right, next problem, 3.6.4. Here he asks us to prove proposition 3.6.14, this is a long problem, and that's because there's a bunch of parts for proposition 3.6.14. This is the proposition where he outlines cardinal arithmetic, so we'll just take it one step at a time. There's a lot of parts to it. So the proof for part A, maybe I should bring up, hang on, maybe I should bring up the theorem just so I can refer to them, because there's so many parts, because it might be confusing if I just show you the proof without showing what I'm proving. Give me 1 second while I do that. Sorry for the dead air. Just give me a second. I just have to find it in my hard drive here. What do I want? 3.6 summary. All right, let me bring this up. All right, so here's proposition 3.6.14, cardinal arithmetic. So here's what part A says, and so I'll just show you what each of the parts say, and then I'll show you my proof of them. So part A says, let X be a finite set, and let X be an object which is not an element of X. Then X union the singleton set containing X is finite, and the cardinality of X union singleton set containing X is equal to the cardinality of X plus 1. So let's show that. Let me make this a little bit bigger here. I'll prove this here. All right, so let X be a finite set, and let X be an object such that X is not an element of X. And just so I have, it's easier to write this, so just let the cardinality of X be n. Then there is a bijection f from the set of natural numbers from 1 to n to x. Define a new function f hat from the set of natural numbers from 1 to n. From 1 to the successor of n to the set X union the singleton set containing X, where f hat of I is equal to f of I if I is between 1 and n, and is equal to X if I is equal to the successor of n. Right, then f hat is a bijection, as is easily shown. I didn't do that here, but it's just show that it's injective and bijective. I just didn't feel like writing it out, but if you can do that on your own if you like. Therefore, since that's a bijection, the cardinality of X union the singleton set containing X equals the cardinality of X, the successor of the cardinality of X, which is the same thing as the cardinality of X plus 1. All right, and that's the proof of part A. All right, let me read out part B, and then I'll show you my proof. B says, let X, Y be finite sets, then X union Y is finite, and the cardinality of X union Y is less than or equal to the cardinality of X plus the cardinality of Y. If in addition, excuse me, if in addition, X union Y is finite, and I'm sorry, I'm looking at the audio. Just I want to make sure that the audio is still going because of what happened last time. But anyway, then X union Y is finite, and the cardinality of X union Y less than or equal cardinality of X plus cardinality of Y. If, in addition, X and Y are disjoint, in other words, X intersect Y is empty, then the cardinality of X union Y is equal to the cardinality of X plus the cardinality of Y. So here's my proof. All right, let X, Y be finite sets with the cardinality of X equal M and the cardinality of Y equal N. I just defining that in terms of new variables, just because it's easier to write that instead of, cardinality of X every time and so on, respectively. Then there are bijections, F from the set of natural numbers from 1 to M to X, and G from the set of natural numbers from 1 to N to Y. All right, part 1, assume that X intersect Y is empty. So we're doing the easy case first. Let H be the function from the set of natural numbers from 1 to N to the set of natural numbers from M plus 1 to M plus N, such that H of I equals I plus M for all I between 1 and N. Then H is a bijection, again, as is easily shown, but I didn't do it here, but just show it's injective and surjective. Next, define the function capital F from the set of natural numbers from 1 to M plus N to the set X union Y, such that capital F of I is F of I if I is between 1 and M, and G of I if I is between M plus 1 and M plus N. Then capital F is a bijection, again, as you can easily show, but I skipped showing that, but just show it's injective and surjective. Therefore, the cardinality of X union Y equals M plus N equals the cardinality of X plus cardinality of Y, right? And then we go to the more complicated case, which is where X and Y are not necessarily disjoint, right? Then X union Y is equal to X union the set difference of Y with X. Also, notice that X intersect the set difference of Y with X is empty. Furthermore, Y minus X is finite, and the cardinality of Y minus X is less than or equal to cardinality of Y. Those two things follow from part C, which we haven't proved yet, but we'll prove them when we get to part C. Therefore, cardinality of X union Y is equal to the cardinality of X union Y minus X, which is equal to the cardinality of X, plus the cardinality of Y minus X, which is less than or equal to the cardinality of X plus the cardinality of Y. And that proves part B, provided that C holds, and it does, because I'll prove that next. All right, part C says this. Let X be a finite set and let Y be a subset of X, then Y is finite and the cardinality of Y is less than or equal to the cardinality of X. If in addition Y is not X, then the cardinality of Y is strictly less than the cardinality of X. All right, so here's my proof. Let X be a finite set and Y be a subset of X. Let F be a function from bijection from 1 to N to X. Then here I'm defining the set A to be the set of all natural numbers in the set from 1 to N, such that F of I is an element of Y. This is a bounded set by exercise 3.6.3. So there's a K in N such that K less than equal N, and bijection G from the set of natural numbers between 1 to K to A. Then the composition F with G from the set of natural numbers 1 to K to Y is a bijection, which implies that cardinality of Y is equal to K, which is less than or equal to N, which is equal to the cardinality of X. Furthermore, if Y is not if Y is not equal to X, or in other words, if Y is a proper subset of X, then there's at least one X in X, such that X is not an element of Y, which implies that Y is a subset of X minus the singleton set containing X, which implies that the cardinality of Y is less than or equal K, less than or equal N minus 1, which is less than N, which is the cardinality of X, and that proves part C. All right, part D next. Right, D says if x is a finite set and f from x to y is a function, then f of x is a finite set with cardinality f of x less than or equal cardinality of x. Cardinality of f. Sorry, let me say this properly. Cardinality of the forward image of x under f is less than or equal to the cardinality of x. One has equality if and only if f is 1 to 1. So let's prove that here. All right, let x be a finite set. And I'm just going to check the audio again just because I'm worried. Okay. I hope it's still working. It looks like it's frozen. I don't know. Okay, let x be a finite set and f from x to y be a function. There is a bijection g from 1 to n to x. Define h from 1 to n to f of x, the forward image of x under f, by h of I equals the composition of f composed with g evaluated at I. If f is injective, then obviously h is a bijection. So that implies that the cardinality of the forward image of x under f is equal to the cardinality of x. And then in the other direction, if the cardinality of the forward image of x under f is equal to the cardinality of x, then h is a bijection, which implies f is injective by my solution to exercise 335. All right. If f is not injective, then there is at least one y in f of x such that f of x1 equals f of x2 equals y, and x1 is not x2. Then f hat from the set x minus x2 to the forward image of x under f, where f hat of x equals f of x, where x is not x1, is either a bijection, in which case the cardinality of the forward image of x under f is equal to the cardinality of x minus the singleton set containing x2, which is equal to n minus 1, which is less than the cardinality of x, or else we can continue this process, which necessarily terminates in at most n minus 1 steps with a new bijection with domain of cardinality less than the cardinality of x, right? And that proves the theorem. All right, next is part E. I told you this was a long problem, but we're almost done with it. Let x and y be finite sets, then the Cartesian product x times y is finite, and the cardinality of x times y is the cardinality of x times the cardinality of y. All right, here's my proof. Let x, y be finite sets, and let f and g be bijections. F goes from the set of natural numbers between 1 and n to x, and g goes from the set of natural numbers from 1 to m to y. Consider the family of sets, x times the singleton set y. So in other words, all these sets have second component fixed. It's a fixed element of y, and the family of sets there vary over all elements of y. For each of these sets, there's a bijection f sub y from 1 to n to x times y, or x times the singleton set containing y, where f sub y of I is equal to the ordered pair f of I comma y. Then the cardinality of x times the singleton set containing y is n for each y and y. Also, since the cardinality of y equals m, there are m sets x times singleton set y. Therefore, the cardinality of the union of x times the singleton set containing y, where y varies over the all the elements of y, is equal to the cardinality of x times y, which is equal to m times n, which is cardinality of x times cardinality of y, which follows from part B. All right, so that's part E. Next, part F. All right, part F says this, let x and y be finite sets, then the set of all functions from x to y is finite, and the cardinality of the set of all functions from x to y is equal to the cardinality of y raised to the power of the cardinality of x. Right, here's my proof. Let x, y be finite sets as above, then the cardinality of x equals n, cardinality of y equals m. Since the set of all functions from x to y is a subset of the power set of x times y, all we need to do is count how many ways we can pair each x and x uniquely with an element of y. Clearly, the singleton set x times y has m elements, so we merely need to count the number of sequences of length n of elements of y. This number is the cardinality of the Cartesian product of y with itself n times, which that cardinality is m to the n, which can be shown by induction, which I do here. So if n is 1, cardinality of y obviously is m to the first power, right? Because it's just the cardinality of y. If the cardinality of the Cartesian product with itself n times is m to the n for n and n, then the cardinality of the Cartesian product of y with itself n plus plus times, or from 1 to the successor of n, or here I called it n plus 1, but it's what I mean here is the successor, right? N plus plus. You can call it n plus 1, right? It doesn't really make that much a difference. Okay, that's equal to cardinality of the Cartesian product of y with itself n times Cartesian product with y, and that's equal to the product of those the cardinalities of those two sets, which is m to the n times m, which is m to the n plus 1, or if you like, m to the successor of n, if you prefer. That implies that the cardinality of the set of all functions from x to y is equal to the cardinality of y raised to the cardinality of x. Okay, that was a long one. Right, next 3.6.5. Right, let A and B be sets. Show that A times B and B times A have equal cardinality by constructing an explicit bijection between the two sets. Then use proposition 3.6.14 to conclude an alternate proof of lemma 2.3.2. Lemma 2.3.2 says that multiplication of natural numbers is commutative. All right, let's go ahead and do the proof. So let f be a function from a times b to b times a, be the function that takes the ordered pair ab to the ordered pair b comma a. Then f of f of ab equals f of a prime b prime, implies that b comma a equals b prime comma a prime, which implies that b equals b prime and a equals a prime. By the way, we defined equality of ordered pairs, so that means that f is injective. Also take the ordered pair b comma a and the set b times a, then obviously f of ab is equal to the ordered pair ba, so f is surjective. Therefore f is f is a bijection. All right, lastly, put ab lastly, let AB be finite sets with cardinalities m, n respectively. Then the cardinality of A times B equals the cardinality of B times A by the above bijection. And proposition 3.6.14 implies that mn equals the cardinality of A times B equals the cardinality of B times A, which is equal to n times m. That implies that n times m is equal to m times n by uniqueness of cardinality, and this provides an alternate proof of proposition 2.3.2, and that's it. All right, 3.6.6, let ABC be sets. Show that the set, show that the sets, the set of all functions from the set C to the set of all functions from B to A, and the set of all functions from B times C to A have equal cardinality by constructing an explicit bijection between the two sets, and then conclude that the cardinalities A to the B to the C equals A to the B times C for any natural numbers A, B, C, and then use a similar argument to conclude that A to the B power times A to the C power is equal to A to the B plus C power. I have a little thing to say about that second part when we get to it, but let's do the first part to start with. All right, let excuse me, let ABC be finite sets with cardinality ABC respectively. Define the function h from the set of all functions from B times C to A to the set of all functions from C to the set of all functions from B to A by, so here we're going to take the function f from the first set to the function f in the second set, such that here I'm using the graph of the functions. So h of the graph of the first function f is equal to the graph of the second function, right, which I have written here out as sets of ordered triples or ordered pairs, right? Then I just show that h is injective and h is surjective, which means, which would mean it's a bijection. So it's injective since if the, h of the function, the graph of the function f equals h of the graph of the function f hat, then the graph of the function f and I don't want to read out these long sets is why I'm saying it this way, but you know, the outputs here are the same, right? For any C and C, that means that the second components for each of the ordered pairs are the same for, you know, the same first component, and that means that f of bc equals f hat of bc for any b and b. So that shows that the function h is injective. Right, part two, h is surjective, since if f is an element of the set, sorry, this should be not lowercase, this should be, whoops, this should be capital B, this should be capital C. So f is an element of that set, then f, again, I'm kind of abusing notation here just because I think I got tired of writing, because this is such a long exercise set. This is the graph of the function f, obviously. Hopefully that's clear. F equals the set of ordered pairs that I have written out here for some g in the second set. The result follows from proposition 3.6.14. All right, so we have, you know, this function h I showed is injective and surjective, which means it's a bijection, and then that means that the cardinalities are the same, right? And then, you know, the result about the natural numbers follows from proposition 3.6.14. All right, and we do something similar for the other property here. The only thing you got to be careful about here, because he doesn't say this explicitly in you know, when he states the problem, here in order for this to work, you need B intersect C to be empty, or in other words, you need B and C to be disjoint sets. But if it is, then it works. So here I'm just doing a similar type of proof. Let H from the set of all functions from the set B to A, a Cartesian product with the set of all functions from C to A to the set of all functions from B union C to A, be the function such that H of F comma G equals, here I'm abusing notation, but I'm just explaining here, so it's because I don't want to confuse anybody. When I say, you know, F union G, well, originally I had written F union G, and actually down here I have it written. What I mean is the graph of F union the graph of G. Hopefully that's clear. Okay, so that's what my function does. It takes F comma, the ordered pair F comma G to the union of their graphs, all right? H is injective since HFG equals H F hat G hat, implies that again, here I'm talking about the graphs, just so it's clear. The graph of F union the graph of G equals the graph of F hat union the graph of G hat, implies that F equals F, sorry, the graphs, right? Graph of F equals graph of F hat, or actually even the functions, right? It implies that the functions are equal to, since the domains of the two functions are disjoint. So if they're not, then you can't conclude that. But if they are, then you can. All right, so that shows that H is injective. Part two, H is surjective, since if F is an element of the set B union of all functions from B union C to, let me just make sure that the audio is still going. Okay, F is a function from the set of all functions from B union C to A, then F is the graph of F is the set of ordered pairs X comma G of X, where X is in B or X is in C, and you can break that up into a union. That's the union of the set of ordered pairs X comma G sub B of X. So here, what I mean by G sub B is the function G, but just considering the elements of B as inputs, right? Union with the set of ordered pairs X comma G sub C of X, again, defined in a similar way. It's just that I'm only considering inputs from the set C for that graph. But that, if you look, that's just the way that I defined H of GB GC. So H is surjective. All right, the result, and then the result follows from proposition 3.6.14. If the set B and C are disjoint. All right. Okay, that's the proof of that one. Next is 3.6.7. Let A and B be sets. Let us say that A has lesser or equal cardinality to B if there exists an injection F from A to B. Show that show that if A and B are finite sets, then A has lesser or equal cardinality to B, if and only if cardinality of A is less than or equal to cardinality of B. Right, here's the proof. Let A, B be finite sets. Assume A has lesser or equal to cardinality of B. Then there exists an injection F from A to B. Then F of A is a subset, the forward image of A under F is a subset of B, which implies that the cardinality of A equals the cardinality of the forward image of A under F, which is less than or equal to the cardinality of B by proposition 3.6.14. Next, assume that the cardinality of A is less than or equal to the cardinality of B. Then there are bijections. So here I'm just defining these bijections. Let F be the bijection from the set A to the set of natural numbers between 1 and M, and G be a bijection from the set of natural numbers from 1 to N to the set B, where M is less than or equal to N. Then the composition G composed with F from A to B is an injection by exercise 3.3.2. And that proves the proposition. All right. Exercise 3.6.8, let A and B be sets such that there exists an injection F from A to B. For example, A has lesser or equal cardinality to B. Assume also that A is non-empty. Show that there exists a surjection G from B to A. And then he says here as a note, the converse to this statement requires the axiom of choice, which he says, see exercise 8.4.3. We're obviously not up to chapter 8, but we will get there eventually, hopefully sometime in our lifetime. Just because it's taking me so long to get through stuff. Anyway, we're not going to worry about the converse. So in this chapter. So here's the proof. Let A be non-empty and let F from A to B be an injection. Fix A in A. Define the function G from B to A, where G of B is defined to be F inverse of B. If B is in the forward image of A under F, and it's equal to A. If B is not in the forward image of A under F, then G is a surjection, since for any X in A, F of X equals B, which is an element of the forward image of A under F, which implies that F inverse of B is X. All right, so that's surjection. All right, next one, 3.6.9. Let A and B be finite sets. Show that A union B and A intersect B are also finite, and that the cardinality of A plus the cardinality of B, is equal to the cardinality of A union B plus the cardinality of A intersect B. All right, here's the proof. Let A, B be finite sets. Then, sorry, I'm just going to readjust here. My leg is falling asleep. And I want to make sure while I'm doing this that I don't sit on the volume knob like I did last time. Okay. Let A and B be finite sets, then the cardinality of A union B is less than or equal to the cardinality of A plus the cardinality of B, and the cardinality of A intersect B is less than or equal to the cardinality of A by proposition 3.6.14. Therefore, A union B and A intersect B are finite. Next, A is equal to the set A minus B union A intersect B, and B is equal to B minus A union A intersect B. Then the cardinality of A plus the cardinality of B is equal to the cardinality of A minus B union the cardinality of A minus B union A intersect B plus the cardinality of B minus A union A intersect B. Now, all of those are disjoint sets, so I can just, the cardinality distributes over the unions here. So that's equal to the sum that I have here, which I can rearrange. That's equal to the cardinality of A minus B plus cardinality of B minus A plus cardinality of A intersect B plus cardinality of A intersect B, which is equal to the cardinality of A minus B union B minus A union A intersect B plus the cardinality of A intersect B. Again, all these things follow from the fact that the sets I'm working with here are disjoint. And then the cardinality of that first set is equal to the cardinality of A union B plus the cardinality of A intersect B, and that's it. All right, 3.6.10, let A1 through AN be finite sets such that the cardinality of the union of the AI for I between 1 and N is greater than n, show that there exists I in the set 1 through n, such that cardinality of A sub I is greater than or equal to 2. This is known as the pigeonhole principle, which you're probably familiar with. Here's my proof. So assume I did this by contradiction. So assume n is greater than the cardinality of the union of the A sub i's, and that the cardinality of AI is less than 2 for all I in the set 1 through n. Then we have n less than cardinality of the union of the AIs, less than or equal to the sum of their cardinalities, the cardinality of the AIs from 1 to n, which is less than or equal to 1 added to itself n times, which is equal to n. Therefore, that implies n is less than n, which is a contradiction. Therefore, the cardinality of AI has to be greater than or equal to 2 for at least one of the AIs. And that's the proof. All right, 2 more problems to go. 3.611 says, let f from x to y be a function between 2 sets x, y. Show that the following are equivalent. So A is that f is injective, and B is whenever E is a subset of x that has cardinality 2, then the image f of E also has cardinality 2. And he says as a note here, note that if x has cardinality less than 2, then the claim in B is vacuously true. Nevertheless, the equivalence still holds in this case. Because of this equivalence, one could refer to an injective function as a 2-to-2 function, and he says this observation is due to John Conway, who I didn't know this until I read this problem, but apparently John Conway passed away in 2020, which is sad. I wasn't aware of that, but this result, he says, is due to John Conway. All right, here's my proof. So first I show that A implies B. So let f from x to y be injective and E a subset of x, where the cardinality of E is 2. Then there's a bijection G from the set 1, 2 to E, and f composed with G from is a function from the set 1 to 2 to the forward image of E under F. It's a bijection, as is easily checked. I didn't do it here again. It's just show it's injective and bijective. It's easy to do. Therefore, cardinality of f of E is equal to 2, and that shows that A implies B. Next, I show that B implies A. So let f from x to y have the property outlined. Again, I just want to make sure that the audio is okay. All right. Let f from x to y have the property outlined in B, then take x hat in x is not equal to x hat, then the cardinality of the set containing x and x hat is 2, which implies that the cardinality of the forward image of that set under F is equal to 2 as well, which implies that f of x is not equal to f of x hat. Therefore, f is injective, right? And that's the proof. Right, so in other words, A implies B and B implies A. So they're equivalent. All right, this is the last problem in chapter 3, and then we're finally up to chapter 4, which I'm excited to get around to do something a little bit different. All right, 3.6.12. For any natural number n, let Sn be the set of all bijections phi from the set of all natural numbers from 1 to n to itself. Such bijections are also known as permutations. Of the sometimes called the set of permutations on n letters, but that's what it is. It's the set of bijections between that set in itself. For any natural number n, show that Sn is finite and that the cardinality of S sub the successor of n is equal to the successor of n times the cardinality of S sub n. He gives a hint here. He says partition S sub the cardinality of partition S sub the successor of n into the successor of n subsets, depending on the value of phi of the successor of n, a permutation phi from the set 1 to n to the set of 1 through n from the set I of all I between 1 and n assigns to the successor of n. All right, and then part B actually follows directly from part A. So I'll read it out here, though. Define the factorial n factorial of a natural number n recursively by 0 factorial equals 1, and the successor of n factorial equals the successor of n times n factorial for all natural numbers n. Show that the show that the cardinality of S sub n is equal to n factorial for all natural numbers n. All right, so for part 1, I used induction. So here, induct on n, base step is n equals 0. there's only one bijection from the empty set to the empty set. Therefore, the cardinality of S0 is 1. Furthermore, there's only one bijection from the singleton set containing 1 to the singleton set containing 1, namely the identity function on that set. Therefore, the cardinality of S1 is equal to the cardinality of the is equal to the successor of 0, which is 1, times the cardinality of S sub 0, which is also 1. 1 times 1 gives you 1, and that works out. All right, then we move on to the inductive step. Assume the property holds for some natural number n. Consider S sub the successor of n. By inductive hypothesis, the cardinality of the S sub the successor of n is equal to the cardinality of, is equal to the successor of n times the cardinality of Sn, which implies that the S sub the successor of n is finite. All right, and then we can partition the set S sub the successor of the successor of n into the successor of the successor of n number of disjoint sets A1 through A sub the successor of the successor of n, where AI is defined like I have written here. Right, this the set AI is the set of all bijections from the set one, set of natural numbers between 1 and the successor of the successor of n to itself, where or such that phi of n, the phi of the successor of n is equal to I. This should be missing a parentheses here. Let me just fix this. Okay. Then S sub the successor of n is the union of the AIs, and the intersections are all empty, and the cardinality of A sub I obviously is the cardinality of S sub the successor of n. So the cardinality of S sub the successor of n is equal to the union of the AIs, where I goes from 1 to the successor of n, which is equal to the sum of the cardinalities of the AIs, where I goes from 1 to the successor of n, which is, since there's the successor of n of those, and they each have cardinality S sub the successor of n, then you get, the result for that. So therefore, this property holds for all natural numbers n, right? And that proves part A. And like I said, part B, the second part, hang on, did I call this 1 or it's, yeah, 1 and 2. So 2 follows directly from part 1. And that's it. That's the, let me just stop the screen share for a second. All right, so that's it, guys. That's the end of chapter 3 in Tau. I'm looking forward to getting around to starting on chapter 4, which hopefully will be a little bit quicker to get through than chapter 3. Chapter 3 was kind of a long one, but we're done with it now. And let me know what you guys think down below. Look out for the video on chapter 4, section 1 coming up relatively soon. And I'll see you guys in the next video. Keep learning until that time, guys.